There we go. So welcome back, everyone. I almost just knocked over my water bottle. Um, this week, we are going to be only working on the quiz. There is no homework notebook this week. It is literally just these problems that we need to go through. Um, I will walk through them pretty thoroughly. So if you understand a problem, I apologize. If you're watching the recording, you can feel free to skip ahead. If you are here in person, I just want to remind you all that this is tricky stuff. People don't normally learn linear algebra at all. And if they do learn it, it's normally in college. So I just wanted to start this with a heads up that it is totally fine if you don't understand it your first attempt or your second attempt or your third attempt or your 10th attempt. It is very, very common to need a second to kind of comprehend what is going on. And I also want to remind everyone that we all learn at kind of different rates. So I'm going to go through it very slowly for those people who need a little bit more practice or a more in-depth explanation. So I do ask that you are patient today and next week, where we're also doing a little bit of math. So I just want to start off with that disclaimer. But beyond that, let's get started. So when you first open the homework quiz, this first question asks, which of these is a valid quantum state? So whenever you see that kind of wording, whether it be valid quantum state or which of these represents a quantum state, when it's asking you if a vector is an actual quantum state, the first thing that should pop into your head is this vector normalized? And remember, we care about this normalization because to be normalized means the vector has length 1. And why do we care that the vector has length 1? Well, it's because of Born's rule. Born's rule tells us that the square of the component gives us the probability of measuring the state that that component represents. So for example, if we squared this number on top here, we would get the probability of measuring the 0 state. If we squared the number on the bottom, we would get the probability of measuring the 1 state. And connecting this back to the norm or the length of the vector, of course, we have a 100% chance of measuring something. We don't know what that something's going to be, but we're going to measure either the 0 state or the 1 state. So having a vector be length 1 is equivalent to saying there's a 100% chance that we'll measure something. If the length of the vector was 2, then we couldn't use Born's rule because then we would have a 200% chance of measuring something, which just doesn't make any sense. So requiring a vector to have length 1 is just the exact same thing as saying our probabilities need to add up to 100%. That is all normalization is. So if we want to check the norms of these vectors, there is a formula that actually comes from the Pythagorean theorem. So the Pythagorean theorem says that if we have a triangle like this that has a right angle, we have two sides. Let's call this length A and this length B. Then the length of this side is the square root of A squared plus B squared. And let's see what that looks like for a vector. So on this axis, I am going to plot, let's say, the contribution of the 0 state or the amplitude of the 0 state. So let's say this contribution is A. And on this axis, I'm going to plot the contribution of the 1 state. So let's call this B. So this would represent the vector A, B. I'm just plotting it like it's an ordered pair or a set of coordinates. And when we plot vectors, we normally draw them like an arrow pointing to that point. But something I want to point out is if I draw this dotted line here, you might notice that this is a right angle. And now we have a triangle where this side has length A, this side has length B. And so if I wanted to find the length of the vector, I would get the exact same result that we got before. It's a squared plus b squared. So that's just a nice visual that shows us that this formula is correct. It actually calculates what we think it's going to calculate. I personally hate memorizing things. And so I am going to show you a bunch of tricks where you might be like, why is he even showing us this? But it's so that you don't need to memorize any formulas or anything. If you remember the Pythagorean theorem, that is enough. All you need to do is kind of remember this picture, and then you will automatically remember how to calculate the length of a vector. So let's apply that to some of these vectors. So this first one, for example, we have a 1 in the top component and a 1 in the bottom component. So the length of this vector would be the square root of this top number squared, so 1 squared, plus this bottom number squared, which is also 1 squared. 1 squared is 1, and 1 plus 1 is 2. So the length of this vector is the square root of 2, which is not equal to 1. So A is not a valid quantum state because its length is not 1, which means we won't be able to use Born's rule to predict probabilities, which is no good. Let's try this out with B. So now we have this vector here, 1/2, 1/2, and we can do the exact same thing. We take the square root of this top number squared, so 1/2 squared, plus this bottom number squared, so again, 1/2 squared. 1/2 squared is a quarter, so we have 1/4 plus 1/4, which is the square root of 1/2. And this is also not equal to 1. You could plug this into a calculator if you wanted. So B is not a valid quantum state either. C is easy because one of the components is 0. So when we do our square root, we're going to have 1 over the square root of 2 squared plus 0 squared, which is 0. So we end up with the square root of 1 over the square root of 2 squared, which is just 1 over the square root of 2, which again is not equal to 1. So A, B, and C are not valid quantum states. Let's keep going with D. D, if we take these numbers here, we have the square root of 5/6 squared plus the square root of 1/6 squared. That's a 6. The square of a square root is just the number, so we get 5/6 plus 1/6, which is the square root of 1, which gives us 1. So D is the valid quantum state here because it is the only vector that has length 1. We could do the exact same thing with E, and I'll do that just to check. So we have the square root of 2 over the square root of 3 squared plus 1 over the square root of 3 squared. We square the numerator, and we square the denominator, so we end up with the square root of 2 squared is 4. The square root of 3 is 3. Plus 1 squared is 1. And square root of 3 squared is 3. And we get the square root of 5/3, which again is not equal to 1. So the only vector out of all of these that has length 1 is option D here. So the correct answer to question 1 is D. Are there any questions about question 1 before we continue? All right. So taking a look at question 2, what coefficient would normalize this vector? So when we're talking about normalizing a vector, we're talking about multiplying it by a number to make it have length 1. So this vector, let's check its length first. So we can take the square root. The first number is 3, so we take 3 squared and add that to the second number squared, which is 4 squared. We can simplify this a little bit. 3 squared is 9. 4 squared is 16. 9 plus 16 is 25. So we get the square root of 25. And then the square root of 25 is 5. So the length of this vector is 5. So how would we rescale this vector to get a vector that has length 1? Well, if we make it 1/5 of the size, then the length of 5 is going to be shrunk down to a length of 1. So what we do is we divide by the length of the vector. You can also think of this like if I have a 12-foot pole and I cut it into 12 pieces, each piece that I end up with is going to be 1 foot long. The exact same thing applies if I have a 100-foot pole and I cut it up into 100 pieces. It doesn't matter. I'm still going to end up with pieces that have length 1. And that is exactly what we're doing here. We are multiplying or dividing a vector by its length to end up with a vector that has length 1. So all we would do is we would multiply by 1/5 to get a vector that has length 1. So this is our normalized vector. You could also multiply this coefficient into the vector to get 3/5 and 4/5. These two are actually the exact same thing, but it's asking what's the coefficient, and so the correct answer, the correct answer here is C, which is 1/5. Are there any questions about question 2 before we continue? All right. Then let's take a look at question 3. Question 3 asks, what is the probability of measuring the 0 state for this vector here? So we're not going to check that this state is normalized. If it tells you that something is a quantum state, there's no reason to not believe them. If we're calling it a quantum state, you can assume it's normalized. We're not going to throw you a curveball or anything. So let's just assume this vector is normalized, which it is, I promise. And to calculate the probability of measuring a specific state, we use Born's rule, which states that to calculate the probability of measuring a specific state, we take the square of the component that corresponds to that state. So just as a reminder, the top number corresponds to the 0 state, and the bottom number corresponds to the 1 state. So we would square this top number here, but there's kind of an issue. If we do the square root of 5 squared, we end up with 5, which is definitely not correct because this says that there's a 500% chance of measuring the 1 state or the 0 state, and that's not possible. So the issue here is we have a coefficient out in front of this vector. And I always recommend, before applying Born's rule, you should bring this coefficient inside the vector. So instead of having this 1 over square root of 6 out front, I would write it as the square root of 5 over the square root of 6. And then I multiply by the bottom number 2, which is 1 over the square root of 6. So I literally just took both of these numbers here and multiplied it by this coefficient to get the 1 over square root of 6 inside the vector instead of outside. And now when we square the top number, square root of 5 over square root of 6 squared, we get 5 over 6, which is about 83%. So you could plug that into a calculator if you don't believe me, but I will tell you it is 83%. So yeah, this problem is really tricky because it points out that if we have a coefficient out front, that is also something that needs to be squared. And so it's a lot easier to remember what we need to do with this coefficient out front. if we bring the coefficient inside the vector to get something that looks like this, and then we can use Born's rule without having to remember to bring the coefficient back or anything like that. It is a lot easier to just bring the coefficient inside than try to remember it and do something extra at the end. So are there any questions about question 3 before we continue? All right. Y'all are doing great. Let's take a look at question 4. Question 4 asks, what is the result of this inner product? So we have a 0. This is called a bra. This 0 here, it's kind of like a backwards ket. And we have 1 over the square root of 8 times this whole mess here. So the cool thing about this inner product is it kind of follows all of the nice rules that like a polynomial follows, for example. So, for example, this is distributive. So it's kind of like I'm applying it here and then I'm applying it here. We can also always bring the coefficients out front. So instead of this 0 bra and then 1 over the square root of 8, I could bring the 1 over square root of 8 out front and then do this. So it would look something like this, plus square root of 5 times the 1 state. So a lot of it, or a lot of the manipulating that we're going to be doing with these expressions comes from something like a polynomial. So if you know how to distribute and put the coefficients out front and all of that stuff, then this is exactly like that. So I already kind of did the first step of bringing this 1 over square root of 8 to the other side of the 0. And now I can distribute these to both of these here. So remembering this coefficient out front, I get 1 over the square root of 8. And then I will get the square root of 3, which I get from here. And I'm going to switch the order with this 0 here. And then I get the inner product of 0 and 0 plus, and then I'll do the same thing here. So I'll bring the square root of 5 out front, and then I get the inner product of 0 and 1. All right, so we have this kind of messy expression, but we can simplify it a little bit. So the inner product of a quantum state with itself is always going to be 1. And the reason for that is because it has length 1. And it turns out that the square root of this inner product, let's say it's like this, is equal to the length. So all of these things are connected. The inner product, the length, normalization, probabilities, all of these things are really, really closely related. And yeah, so that's another thing we can remember is that the inner product of a quantum state with itself is always going to be equal to 1. So let's write this on the next line. We get 1 over the square root of 8 of root 3 times 1, which is still root 3. And then the square root of a state, a quantum state with the state pointing in exactly the opposite direction on the block sphere is going to be 0. So because the 0 state and the 1 state are complete opposites, this is going to be 0. And so the square root of 5 times 0 is just going to be 0. So the result of this inner product is the square root of 3 times 1 over the square root of 8, which is square root of 3 over square root of 8, or just the square root of 3/8. So the correct answer to this question is C, the square root of 3 over 8. I don't know why my mouse is so slow. But are there any questions about this question before we continue? What is the vector form of the zero bra? That is a great question. So the vector form of the zero bra is actually just a sideways zero vector. So it would look something like this, where instead of the two numbers stacked on top of each other, the two numbers would be side by side. And this is really cool because the inner product for vectors is just matrix multiplication. So this is the vector form of this inner product here. And I would just do the exact same thing. I would multiply across this row and down this column, and I will end up with the number 1. So yeah, the vector form of the zero bra is similar to the vector form of the zero ket. It's just turned sideways. Great question. Does that mean you can't add them together? That's absolutely correct. There is no such thing as the zero bra plus the 0 ket or something. It's like trying to add together, like, I don't know. What are two things you might try to add together? I don't know. I can't think of an example. But it's like trying to add together 1 plus this vector or something. It just doesn't make sense. What you're asking cannot be done. In terms of Python, it's like trying to add together an integer and a string. That'll give you an error. Those are two completely different things, and we can't add them together. So yeah, there are a whole bunch of wacky combinations of bras and kets and stuff like that, but we actually can't add them together. That's a great point. All right, so let's take a look at question 4. Or no, question 5. What is the probability of measuring a 0 in this state given here? So Born's rule for kets is actually really nice because it says that the inner product of two quantum states gives us the probability of not the inner product, the square of the inner product of two quantum states gives us the probability of measuring that state. So for example, if I wanted to find the probability of measuring the 0 state, I would take the 0 bra, which is the state we want to check the probability of measuring. So this is the state we want probability of. And then on the right, we put the state that we are measuring. So in this case, we will have 1 over the square root of 8 times the square root of 3 times 0 plus the square root of 5 times 1. And then all of this is going to be squared. The square is the same for vector representation or ket representation. You're always going to have that square. Born's rule tells us, however we're calculating this, we need to take the square. So the way we would go through this calculation is the exact same as the previous problem. So we can bring these coefficients out front if we want. This time I'll do it slightly differently. I'm going to distribute this square root of 8 first, just so I could show you a couple different ways we could do the same thing. So I'm going to keep my 0 bra here. I'll multiply this first term by the square root of 8. So we'll get the square root of 3 over 8 times 0. And now I'll multiply it by the square root of 5. We will get plus the square root of 5 over 8 times the 1 state. And this is all still squared. Now I can distribute this 0 over to both of these kets. And I will bring this square root of 3 over 8 out front. So square root of 3 over 8 of the inner product between 0 and 0. And now we'll do the same thing with this one state here. So square root of 5/8, just bring that coefficient out front, times the inner product of the 0 state and the 1 state. Again, this is squared. So again, what is the inner product of 0 and 0? Can anyone tell me that? That's a parentheses, sorry. Yeah, we end up with 1. So we get the square root of 3/8 times 1, which is just the square root of 3/8. And then what's the inner product of the 0 state and the 1 state? Yeah, it's 0. So this term actually goes away because when we multiply something by 0, it's 0. And so all we are left with in the end is the square root of 3/8 squared, which is 3/8. So the probability of measuring the 0 state, if we had this monstrous state up here, is 3/8. So the correct answer is B. B. So are there any questions about problem 5 before we continue? All right. I will clear this. And let's take a look at question 6. Question 6, I can already tell you, is going to be a little more annoying because there are a couple more steps, but it is nothing we can't handle. So there are 2 ways to do this. One of them relies on you memorizing some other inner products, like the inner product between the minus state and the 0 state. And the other one just requires you to remember the ket representation of the minus state. So I'm going to kind of do a mix of both, where I'm going to calculate this inner product separately, and then we'll plug it in if it pops up in here. So let's see if it pops up there. So what we're going to do is, as usual, or I guess same as what I did last time, I'm going to distribute this in here. So I'll get the inner product of the minus state with the square root of 3 over the square root of 8 times the 0 state from multiplying these two, plus the square root of 5 over the square root of 8 times the 1 state. And then I can distribute again with this minus state. I'll apply that to both terms here, and I will bring the coefficient out front. So the square root of 3/8 times this inner product plus the square root of 5/8 times this inner product. All right, so we've gotten to a point where we have this inner product between the minus state and the 0 state, and we need to figure out what this is. But the cool thing about this minus bra is it is the exact same kind of representation as the minus state in kets, just with the kets flipped into bras. So literally, we can take, let me write the ket form of the minus state first. So the minus ket is equal to 1 over the square root of 2 times the 0 ket minus the 1 ket. This is the ket representation of the minus state in terms of the 0 state and the 1 state. So if I wanted the bra representation of the minus state in terms of the 0 state and the 1 state, I would keep this 1 over square root of 2. I'm sorry, it's kind of hard to see. And then I would just flip these kets into bras, and I get the correct representation here. So how does this help us? Well, if we rewrite this in terms of the 0 state and the 1 state, we end up with something that looks like this. And that's something we know how to do, right? We just need to distribute to get an inner product again. So to do this, we have 1 over the square root of 2 out front, and I'll leave it out front. And then we get the inner product between 0 and 0, which comes from this and this. And then I get a minus sign from right here, which I'm going to erase so we don't get confused. And then the inner product between the 1 state and the 0 state. So how did I know what order to put the 1 and the 0? Well, the 1 started on the left, so it should stay on the left. And the 0 started on the right, so it should stay on the right. That's how I remember it. We can't just switch things around unless they're numbers. But bras and kets are not numbers. So we can't just switch their order around however we want. Okay, so once we did this, we now have some inner products that we know how to evaluate. So we have 1 over the square root of 2. The inner product of 0 and 0 is 1, minus the inner product of 1 and 0 is 0. So minus 0. So our final answer is 1 over the square root of 2. This is our long-winded way of saying, oops, not that. This is our long way of saying that the inner product of the minus state and the 0 state is 1 over the square root of 2. Now, another thing that you yeah, actually, let's not do it. Let's do this computation again. I think it's good practice. So we are going to repeat this exact same process with the inner product between the minus state and the 1 state now. So the inner product between the minus state and the 1 state is, we're going to have 1 over the square root of 2 of this 0 bra minus this 1 bra, all applied to the 1 state. Yeah, so we're not done with the problem yet. There's still a couple more steps. We are just figuring out what these inner products are in this expression, and then we'll simplify it all at the end. Remember, we only did this as an intermediate step because we don't know what the inner product between the minus state and the 0 state is, and the minus state and the 1 state is. So 1 over square root of 2 isn't our final answer. We'll get to the final answer in just a second. So we will distribute again here, and we get 1 over the square root of 2 out front. We get the inner product between the 0 state and the 1 state from this here, minus the inner product between the 1 state and the 1 state. Again, we can simplify this. This is going to be 0, so we don't need to worry about it. The inner product between the 1 state and the 1 state is 1. So we get 1 over the square root of 2 times minus 1, or negative 1 over the square root of 2. So that is what we can plug in here. And we get square root of 5 over 8 times negative 1 over the square root of 2. All right, are there any questions? Here is a good point to pause before we wrap up this problem. But I want to make sure y'all are following so far. So are there any questions about how I got to this point from, I guess, the question? All right. Then all that's left to do is simplify. So we have here the square root of 3/8 times 1 over the square root of 2. Since this is in the denominator, we can just multiply these two, and we end up with the square root of 3 over 16. So I just multiplied 8 by 2 since they're both in the square root. And I could do the exact same thing over here. I'm going to put a minus sign so I don't have to worry about this minus sign here, but I do the same thing. There's a square root of 8 in the denominator here, and a square root of 8 in the or a square root of 2 in the denominator here. So I'll end up with 5 over 16 inside the square root. I can simplify this a little bit because 16 is a perfect square, right? So the square root of 16 is 4. So I could rewrite this as the square root of 3 over 4 minus the square root of 5 over 4. Or, excuse me, I could write this as the square root of 3 minus the square root of 5 over 4. If we zoom out, that should be an option we see. Yes, it is option D, is the square root of 3 minus the square root of 5 over 4. So are there any questions about this problem before we continue? Anything in square roots, you can do operations with each other. Not quite. Like you can't add things in square roots, for example, like the square root of 8 plus the square root of 3 does not equal the square root of 8 plus 3, for example. But multiplication is kind of special. You can multiply and divide things inside the square root as long as they both have the square root. So the square root of 8 times the square root of the square root of 8 times the square root of 3 is the square root of 8 times 3. That you are allowed to do. So it's only multiplication and division that you're allowed to do inside the square roots. Yeah, we can also just say from now on that the inner product of the minus state and the 1 state is 1 over the square root of 2. That's also correct. Yeah, there's also another thing you can remember that has to do with complex numbers, unfortunately, but it has a pretty simple form. The basic idea is that if I have two quantum states, let's call it A and B, I don't know what these two quantum states are, but the inner product of state A with state B is equal to the inner product of state B with state A, but you have to do the complex conjugate. Don't worry about the complex conjugate because we are not working with complex numbers. So for now, you can just think that the inner product of A and B is equal to the inner product of B with A. So let's apply this to our inner product between the minus state and the 1 state, for example. This is equal to the inner product of the 1 state with the minus state. And what does this extract here? What information does this extract? Well, it takes the minus state and it extracts the amplitude of the 1 state, which we should know off the top of our head, right? Does anyone know what the amplitude of the 1, or maybe not off the top of our head, but if we write down the vector, we can figure it out. The vector looks like this. So if we remember the vector looks like this, what should this inner product represent here? Or what value should it be? We're extracting the amplitude of the 1 state inside the minus state. And yeah, that's exactly what we get as this coefficient here. It's negative 1 over the square root of 2. That is the amplitude of the 1 state in the minus state. So this is the answer that we got before, but conceptually, it is connected. This number that we got here when we did this inner product here is connected to this amplitude of the 1 state and the minus state. So in general, what I wrote here, is not true. This complex conjugate will kind of throw in a minus sign sometimes. But because we're not working with complex numbers at all this semester, you don't really have to worry about that. So you can just switch the order if it makes the computation easier, which sometimes it does. Sometimes it does not. Yeah. So are there any questions about that before we continue? Yeah, you got lost in the amplitude. Absolutely. So the amplitude is just the coefficient. So another way we can think of this is in the ket representation, right? So let's write this ket representation here. If I asked you what was the amplitude of the one state in this representation, could you tell me what the amplitude is here? The amplitude of the one state. Remember, there's this pesky coefficient out front. Don't forget about the coefficient. It's also okay to say you don't know. Don't know. Okay. The amplitude is just the coefficient in front of that ket. So the reason I told you to remember this is because this is also part of the coefficient. And so the coefficient in front of the one state is -1 over the square root of 2. That is what we're talking about when we're talking about amplitudes. It's just these things that we're multiplying these kets by. So when I say the amplitude, when we take the inner product, all we're doing is extracting amplitudes. So if I took the inner product with 1 here, then I'm extracting the amplitude or the coefficient of the 1 ket, which just so happens to be this -1 over the square root of 2. Does that make a little more sense? Or I could try to explain it a different way. I'll just need a second to think. Yeah, amplitude is the exact same thing as the coefficient of a ket. Those two things are the exact same. We call it amplitude because it's called a wave function, right? So a wave function comes from waves, and waves in physics have amplitudes, which just says how big or small they are. And so we're kind of applying that to these wave functions now, because the coefficient tells us how big or small the contribution of that state is. So we're kind of using some terminology from regular waves for quantum waves. All right. So, yeah, no problem. Let's continue to question 7. Question 7 is a matrix multiplication problem. So let's remind ourselves how to do this. There are multiple ways to do this, but what I am going to do is a method that I've seen students really like. If this method doesn't really make sense to you, and you have another way you like to do it, that is totally fine. But I like to draw these arrows here. So the arrows tell me that I'm going to multiply across this row here and down this column here. And I remember where to put an arrow because I can't put sideways arrows here because there's not enough space. So the horizontal arrows that tell me I'm multiplying across rows goes all the way to the left here where I have space. And the arrows pointing down must go over here because I already put my horizontal arrows, I guess. And so to calculate the top component, which comes from the fact that I drew my arrow across the top row. Let me undo this, sorry. I calculate this number here times this number here. So moving away from the arrows, it's the first number I bump into. So I do 1 times 1. And then I add that to this number here times this number here. And I'll turn it into a house so we know what's matched with what. I don't know. So this 0 corresponds to this 0. So plus 0 times 0. Now that's the top component. For the bottom component, I could do the exact same thing. I'm going to switch the color to blue, but now I will go down this row and this column here. And I do the exact same thing. I take this number here, which is the first number I bump into when I follow this arrow, times this number here. So I get 1 times 1. And I add that to, I'll just do a circle this time. This 0, which is the second number I bump into, times this 0, which is the second number I bump into. So what we end up with is 1 times 1 plus 0 times 0, which is 1. And then 1 times 1 plus 0 times 0, which is also 1. So these arrows help me kind of figure out what I'm supposed to be multiplying. And they also tell me what component I am solving for. Because that is something that always confused me when I was learning this stuff is, okay, I'm multiplying and adding a whole bunch of numbers, but what number in the result am I calculating right now? If I put the arrow in the first row, then I'm calculating the number for the first row. If I put the arrow in the second row, then I'm calculating the number for the second row. It's just a lot easier for me to keep track. Yeah, this is how I still to this day, I draw arrows on every matrix. I try to multiply in every vector and stuff like that. Yeah, it just helps me keep track. So the correct answer here is the 1, 1 vector, which if I zoom out, the correct answer is A, which is this 1, 1 vector. So are there any questions about question 7 or how I did that matrix multiplication or anything like that? Yeah, this method, I don't think it was talked about during the lecture. I believe you talked about it in terms of a dot product, maybe? Is that right or wrong? Yeah, a dot product between vectors. I don't really remember how you did it in the lecture. But are there any questions about this method where I drew the arrows and I did that multiplication stuff? If you like the other way better that you learned during the lecture, it is totally fine. But there are a whole bunch of ways to do the same thing. So I want to give y'all options. Is that a gate or just a matrix? This is just a matrix. In order for it to be a gate, it has to satisfy a certain property. It has to be what we call unitary. I'm not going to bother telling you the definition of this because honestly, it doesn't matter for us. But this matrix is not unitary, and so it can't be a quantum gate. All right, so if you want to look up unitary, you can do that. I will type it out in the chat, I guess, so you could just copy and paste it. Or maybe I'll look up the Wikipedia page. Unitary. Unitary matrix. Usually there's like a simple English one that gets rid of the messy definitions, but this is a Wikipedia page that talks about unitary matrices. It's probably going to be difficult to understand. So if I have a little extra time after and you have any questions, I'm more than happy to answer that. But just to get through the problems here, I'm going to continue. All right, question 8. We're doing another matrix multiplication problem. So let's draw the arrows again. So I'm going to be multiplying across the top row. Oops. Oh my gosh. Sometimes when I press a button on the pen, it just like keeps drawing and I don't know how to stop it. There we go. I think I did it. Okay, so across this top row here, I'll multiply down this column. And if I'm multiplying across the top row of the matrix, then I'm solving for the top number in the vector. So I will start off, I take this first number in this row and multiply it by the first number in this column. So I get 1 times 1. And I add that to the second number in this row times the second number in the column, which is again 1 times 1. Then I'll change colors again, and now I will multiply across this row and down this column, and that'll give me the number on the bottom because I'm multiplying across the bottom row. And so I'll end up with this 3 times this 1. So 3 times 1 plus this 5 times this 1. And so I can simplify this a little bit. 1 times 1 plus 1 times 1 is 2. And 3 times 1 plus 5 times 1 is going to give us 8. So that is the result of multiplying this vector by this matrix, is 2 and 8 as our components. Are there any questions about how I did this matrix multiplication here? Let's just record the right answer. It is 2, 8, which is B. Oops, shouldn't have erased that so soon. It's going to be hard to line it up again, I guess. Something like, there we go. All right, if there are no other questions, then let's continue. Question 9, oops, wants us to perform the following operation. We want to apply the x gate to this messy state here. Again, we can distribute the x gate. We can pull numbers out of x gates and stuff like that. So I can pull this 1 over the square root of 10 outside of the x gate here, which is what I'm going to do. All right. And let me put fancy things on the x so we can tell it's an x and not just me multiplying. But now we can distribute the x. So I'll apply the x gate here, and I'll apply the x gate here. And I'm going to switch the x and the 2. So it's going to be 2 times the x gate here applied to the 0 state plus square root of 6. Apply the x gate here to the 1 state. And now we can just use what we know about the x gate, that it sends the 0 state to the 1 state and the 1 state back to the 0 state. So 1 over the square root of 10. 2, applying the x state to the 0 state gives us the 1 state plus the square root of 6. And applying the x gate to the 1 state gives us the 0 state. So we're just using what we know about the x gate, how applying the x gate to the 0 state gives us the 1 state, and applying the x gate to the 1 state gives us the 0 state. And this is our answer here. So we just need to make sure we are getting the right coefficients and stuff. So A, that doesn't seem to match our answer. B doesn't seem to match our answer. C, we don't have plus states and minus states in this, so that's not right. In D, we have the square root of 6 times 0, which we have here, plus 2 times the 1 state, which we have here. And then E is the same thing as the state that we're given. They just switched the terms around to try and trick us, but we could not be tricked. The correct answer is D. So we could switch these terms around to write it that way. We just switched the place of the 1 state and the 0 state. So I could do the square root of 6 times the 0 state plus 2 times the 1 state. Addition, we can switch back and forth. We're totally allowed to do that. So I just switched the square root of 6 times 0 and 2 times the 1 state to get option D here. Are there any questions about that before we continue? All right, then let's take a look at this last question. What gate would have this effect here? So it's saying when we apply the gate to this state here, we get this state. And so does anyone notice what changed about this state here? What's the difference between the input state and the output state? Yeah, there's a phase difference. So this plus sign just turned into a minus sign. That is the only thing that this gate changed. So what we can do is we can go through all of the steps that we did before to distribute this gate to the 0 state and the 1 state, and then we figure out what effect the gate had on the 0 state and the 1 state. So I'll bring the 1/3 out front here. So 1/3 of the gate applied to 0 plus square root of 2 times 1. Now I'll distribute this gate here and here. I get 1/3 of the gate applied to the 0 state plus the square root of 2 gate applied to the 1 state. All right, so now all we need to do is match the effects that we have here. So you'll notice that the gate applied to the 0 state has coefficient 1. And the only state we have with coefficient 1 here is the 0 state, right? So we know that the gate applied to the 0 state just has to be the 0 state. In other words, the gate does nothing to the 0 state. What about the 1 state? Well, we have a coefficient of the square root of 2 here. We have a coefficient of the square root of 2 here. But there's a minus sign that has to come from somewhere. And so it must come from us applying the gate to the 1 state. In other words, the gate applied to the 1 state has to equal the minus or -1 times the 1 state, because otherwise this minus sign won't pop up anywhere, because we have a plus sign down here, we have positive square root of 2, so the only place that minus sign could have come from is applying the gate to our 1 state. And so does anyone recognize these two rules here? What gate keeps the 0 state the same but flips the phase of the 1 state? Yeah, this is the Z gate. So the gate that transforms this first state into the second state is the Z gate. So the correct answer here is this third option, which is Z. Are there any questions about how I figured this problem out? All right. If not, you all are free to submit your homework quiz, get that nice 10 out of 10. I will stick around for a few minutes to answer any questions people in the Zoom call have, but people watch it. Oops, did I mark an answer wrong? See, this is why I started submitting them, is because, yeah, I got one wrong too. Oh, I clicked the wrong answer. Okay, so sorry. For question 6, I forgot to simplify a little bit, right? Because, oh no, I clicked D, but I do actually remember us getting 4 in the denominator. So I just said it wrong. We got C, square root of 3 minus square root of 5 over 4, but for some reason I clicked that the answer was D, and I probably said that the answer was D as well. So the correct answer is not D. It's C, which we totally had written down, but when I went to click the right answer, I clicked the wrong answer. So yeah. So the correct answer for question 6 is C. I'm so sorry about that. Can't believe I did that. Yeah, so I don't really want to go back through and resubmit it all, but you can if you want that extra point, which you all deserve. Um, yeah, okay. I'm glad I got that on the recording though. So recording people, goodbye. I will see you next week. Um, yeah, have fun with more math.